In this lesson, we're going to be looking at graphical processing units, or GPUs. Now, for any gamers out there, you're probably very familiar with what GPUs do and the power behind them, but we're really going to start to look at what they actually really are, and also what alternative uses we might have for them other than playing the latest games. So we need to understand what the GPU is and how it can be used for concurrent programming. So remember, in a previous lesson, if you want to check that out on my YouTube channel, we've looked at what we mean by parallel processing and also how we think concurrently. So GPUs is kind of like part of that puzzle. So we're going to kind of look and recap and think about parallel computing and understand the differences between GPU and other CPUs, because they are very, very different devices. So the link on the screen, which I'll include in the description as well, is just looking at the differences between CPU and GPU by our good old friend Linus. I can't explain any better than that, so I'm just going to let him do that job. So do watch that video. It is really, really good. So the key differences that you need to be aware of is a CPU is a general purpose processor. So what do you mean by that? Well, it can be used for anything you can think of. You can play a game, you can write Word documents using it. It's designed to run any application under the sun. GPUs, on the other hand, are very, very, very specialized. Okay, they're not designed to run any old application. They are very much focused on high-end floating point number crunching. So CPUs tend to excel at integer maths. Now, most general purpose computing is integer based, not all of it obviously, and CPUs will have a floating point unit, of course they do. However, GPUs excel at floating point maths specifically because that's the kind of maths that tends to be used in 3D models and kind of games. CPUs can contain 1 to 8 cores. This PowerPoint is a little bit old, so you know, we can easily get more cores than that nowadays, 12, 14, 16, all those kind of numbers. Okay, so along short of it, the number of cores is relatively, compared to a GPU, very, very small. Whilst a GPU will have many, many, many floating point units that will work on different parts of data at the same time. Okay, so they're going to have a larger number of cores. CPUs will allow multitasking. What we mean by that is you can have multiple processes running at the same time. These can be running on different instructions. Now, for those who kind of watched my video about parallel processing, this is essentially multiple instruction, multiple data. Okay, so you run on 2 different programs at the same time. And also those programs can be swapped in and out really, really quickly through multitasking. GPUs, on the other hand, will perform a transformation on polygons, which are part of models. So what that really means is that they are going to be working on different parts of data at the same time. So very much a single instruction, multiple data kind of approach, okay, which is very, very different to the kind of parallelism that you get inside a CPU. So here's an example graphics card. Okay, the Radeon RX 480. Now, I'm fully aware that this is an oldish card by modern standards. However, one thing I want to draw your attention to is the number of compute units, so kind of highlighted there on the screen. The number of compute units is 36, which is much, much, much higher than even the top-end processor you can buy for your desktop. So straight away, you can see one of the core differences. They have a larger number of compute units than a CPU will have. So GPUs, as we've already looked at, are specialized devices. They're not designed for general purpose computing, unlike CPUs. So the instruction set, i.e. the instructions that they can run, are very specialized towards 3 kind of key areas. The first one is trigonometry, so trig operations like sine, cosine, things like that. Those are used quite extensively in 3D modeling. Giant or floating point operations, and also 3D graphics operations. So these kind of calculations are what they will specialize in. This is what they're good at, and this is what they do really, really quickly. So any problem that can make use of this type of number crunching effectively can be coded to use the GPU. So although 3D graphics makes use of that, obviously 3D graphics is 3D graphics. It has lots of floating point operations, it uses lots of trig. However, there are other problems which exist, for example, like Bitcoin mining, which require these types of instructions. And because they are massively parallel and they can work on many parts of data using a single instruction, so SIMD, they work really well for these other types of problems. So single instruction multiple data is what they are really good at. So they're designed to work on lots of pixels, lots of textures, all those kind of things where there is one thing you want to do with them, maybe rotate them or scale them, whatever it happens to be, but you want to do it on every single part of the image, every single part of the model, every part of the scene, etc, etc, etc. So any problem which requires this approach can benefit from using GPU. So GPUs work on assembly, so every core runs the exact same instruction, but it performs it on a different piece of data. So although they have multiple cores, they cannot run in multiple instruction, multiple data. They're not designed for that. Each core uses specialized instructions. So again, this is one of the key differences between GPU and CPU. So some of example uses you might have, so data mining, for example, GPUs can work on SIMD, which is ideal for data mining, because if you think about it, we have lots and lots and lots of data. Because we have lots and lots of data and we want to do the same statistical calculations, for example, on them, we will need that high level parallelism that we can get with GPU. GPUs also have a very high memory transfer rate. So what we mean by that is in order to get all those textures into the graphics card so you can display the wonderful 3D games that you play, it needs to transfer those very large images incredibly quickly to the graphics card. As such, they specialize again in very high memory transfer rates. And this is ideal for data mining, where we have to actually get all that data that we want to mine into this GPU in order to actually process it. So they have more cores than a normal CPU, means they can process more data at once. So they are absolutely ideal for data mining. Same goes for any form of modeling. So you might have a simulation running where there's lots and lots of individual things which all do the same thing, or have the same kind of patterns. This might be molecular modeling, where every atom is going to be following the same set of rules, but needs to have different data calculated on it. It might be, we're talking about airplanes and airplane simulator, all flying in the sky. They're all going to be flying the exact same way, i.e. running the same instructions. However, they'll be working on different data. So those are two classic. So because GPUs are a bit of a funny thing to get exam questions on, what I've done is I've put some exam questions in this video, and what I'm going to do is I'm just going to read the question out and I'm going to go through the mark scheme. So you may wish to kind of pause the video after each question and have a go at it, and then just see if you're right in the video. So a game company decides to release a new video games console. The console will use a modified version of an operating system called Linux. Describe two functions an operating system might be expected to carry out on the console. Now, when you answer this kind of question, okay, there's lots of things that the operating system does. What you have to do is work out which ones are the most useful in a video games console. Okay, you don't just simply write any ones you can think of. You must link your answer back to the question and the context of the question. So let's look at the marks. What I mean. So it provides a user interface. Okay, so that's one of the core elements of an operating system. This will allow the user to load the games up, to change their settings and things like that. So you think about your PlayStation or Xbox, when you boot the computer up, the console up, you'll get that kind of screen, won't you, where you can choose your apps, things like that. That's been managed by the operating system within the console, ergo that is one of the viable answers. So it allows you to control hardware, such as graphics card, games controllers. Specifically, hardware control is very important for a games console because we will have those kind of game pads which you can actually use to interact with it, and obviously the graphics card becomes incredibly important as well. So acts as a platform for which software can be run, such as games and apps. So that enables these games to actually be launched, loaded from storage devices into RAM and run as you would normally run them. And finally, control access, so different users can access the system and have their own data, scores, achievements, save games, things like that. If you think about most games console nowadays, they'll allow you to select who is playing, because you might have a console which is shared between different people and you want different save games for those different people so you don't accidentally overwrite each other's progress. Linux is open source. Explain how Linux being open source would benefit the games company. Little tip on this question, when you do paper 1, you will have questions like this which randomly appear in a different topic. So for example, you might be starting to talk about the von Neumann architecture and all of a sudden you get a question about the legal, ethical, moral implications of computer science. You might be doing a question on hash tables and all of a sudden they throw in an operating system question. This will happen and they will link topics together because they assume you know how to start to link these topics together in your head. So you won't be thrown. For example, when talking about a GPU question, all of a sudden, bang, you get an open source question. As well as CPU, the console contains a GPU for 3D graphics. Explain why a GPU is more suitable than a CPU for this task. So let's look at the mark scheme for those two questions. First of all, this means that a lot of the core functionality they need is already available. So the company just has to make amendments and additions specific to the system, saving them time and money. So let's think of a real world example of this. Android is a classic example where you have a base version of Android and different companies like Samsung, Huawei and all the others, they will take that base Android and add upon it their own kind of take on the user interfaces and their own little bits and bobs of software, etc. That makes their phones a bit more unique, but it's still based on the same stuff. So all the kind of core multitasking, the core features, the keyboard, all those kind of like basic Android features are already been done for them. They don't have to code that themselves. Okay, this obviously allows them to personalize the phone for their company, but also it massively saves them time and money, so they don't have to write an operating system from scratch. Looking at the GPU question, CPUs are general purpose, as we've already really focused in on, whereas GPUs are designed specifically for graphics. Now, they are designed for graphics because they have the word graphics in the title, but obviously they can be used in more generic purpose. Now, it's important to remember that in this context of the question where it's talking about a games console, graphics is going to be the most important thing you can do. Okay, you're not going to be doing Bitcoin mining on your PS4, for example. So they're going to have built-in circuitry instructions for common graphics operations. GPUs are able to perform an instruction on multiple pieces of data at one time. So that's single instruction, multiple data idea. Often we want to do this when processing graphics, i.e. transferring points of a polygon or shading pixels. Okay, so remember inside a 3D image, you're going to have all the models which are made up of polygons. You're going to have all of the textures with their pixels, and you're going to have the lighting and the shading and all that kind of stuff. All that is massive amounts of number crunching because there's lots of calculation to be done, but it's the same calculations. Ergo, single instruction, run on many pieces of data. This means they can transform on-screen graphics much quicker than a CPU can because they can do that massive amount of parallelism, which a CPU just can't do. Next question. Explain 2 reasons why games designed for other companies' consoles may not work on this machine. Now, this question is a little bit odd because actually it's really getting you to think very carefully about architectures now, okay? RISC and CISC and all those kind of things, and also the idea behind compiled programs. So this is a subtly difficult question. The mark scheme. So different console makers will use digital rights management, DRM, to protect games from being run on anything other than their machines. Now, DRM is not necessarily something that you might have learned on the course. It certainly is a thing and is correct, But bear in mind, with questions like this, you may not always get every bullet point, okay? And that's fine, it's okay, as long as you get enough to get full marks, it's not a problem. However, you might have covered DRM when we've been looking at the legal moral aspects of computer science, and if you haven't, well, maybe now's a good opportunity to have a little bit of read up on it to get some ideas what it means. Different consoles will have different processors and have their own instruction sets. So basically, different consoles will have their own custom built CPUs. So the CPU you find in the PlayStation is very different to the one you find in Xbox. And this makes perfect sense because they're designed and created by two completely different companies, and they're not going to be working together to design these consoles. They're in direct competition. So it makes sense that they are different, that they have different instruction sets. They might even be different architectures completely, so it might be RISC and CISC. It depends. Different consoles will have different operating systems, and so games may be dependent on libraries in one operating system that doesn't exist in another, or make different system calls. So the operating systems that these things run on are responsible for getting things on the screen, for doing notifications, for saving things in the cloud, all those kind of common features you find inside a modern computer console, games console. Because of this, how the game programs will access those kind of libraries will be different, because they are different. Okay, the way you save games in the PlayStation is very different to how it works in an Xbox. Okay, as you would expect. Therefore, you can't rely on the program just running straight off the bat, even if it is using the same CPU, because the calls to the operating system will be different, because the operating systems are inherently completely and utterly different. And finally, games might even be on a different media. Okay, so a classic example of this is Switch versus PlayStation, or Switch versus Xbox. Okay, the Switch comes on a little tiny little, almost like an SD card, solid state kind of thing, whilst obviously Xbox and PlayStation will come on a Blu-ray disc. That is fundamentally different. Ergo, if I wanted to run a PlayStation game on my Switch, well, I need to find some way of getting a Blu-ray onto a solid state kind of cartridge. That's not as easy as you probably would imagine, even if I could solve all the other problems beforehand. So I don't always add subject clarification at the end of my PowerPoints. However, I think for GPUs, because it's not obvious what exactly they want you to talk about, it's well worth kind of going into it. So if you're not sure what this is, if you go on the OCR website, you can find a section under the teaching section called subject clarification. Although it's aimed at teachers, I would suggest all students have a little read over it. Okay, it's not written in teacher talk. It's actually really clear about what you need to know for every single topic on the A level. And it was an absolute godsend for us teachers, because we were floundering a little bit in the first few years of this course, because we weren't sure exactly how much detail we were supposed to go into it. So for some topics we went into too much detail, and some topics were not enough. So candidates need to understand the purpose of GPUs and what applications they're used for. Candidates need to understand how GPUs are used to aid graphics, but also of applications, for example, modeling, data mining, etc. Okay, so that's kind of making that clear, that you need to know that GPUs can be used for other things other than playing games. Candidates should also understand the benefits of using GPUs and why they suit certain tasks, special instructions, multiple cores, and SIMD. So we've talked about all of this in this PowerPoint, but I wanted to show you this because that way you know exactly why I've introduced the topics as I have them. So hopefully that will make learning this topic a little bit easier for you.